Good afternoon, everyone. Thanks for joining the ITRI MMSL 2025 Intelligent Mechatronics Online Forum. We're delighted to have you with us. The theme of this year's forum is Next Generation Intelligent Mobility and Manufacturing. The event will explore the latest innovation shaping the future of vehicles and the next generation factories. Now let's take a look at today's agenda. As shown, today's agenda includes 3 10-minute speeches. During this time, the QR code for our survey form will be shown on the screen. Please take a few minutes to fill it out, as your valuable feedback is important to us. If you have any questions, please feel free to leave comments. We have also shared the link to the survey form in the description below. For those who are unable to stay with us throughout the event, please let us know your feedback. We will share today's presentation files upon receiving your feedback. Great, let's get started. Let's welcome Dr. Peng Yang, Deputy General Director of ITRI MMSL, and Karen Ma, Deputy International Affairs Officer and the representative of ITRI Southeast Asia Office to deliver the opening remarks.
Esteemed participants, a warm welcome to today's online forum. My name is Peng Yang, Deputy General Director of Mechanical and Mechatronic System Research Laboratories, or MMSL, at Industrial Technology Research Institute, or ITRI, in Taiwan. We are delighted to have you join us as we embark on an exciting journey into the world of intelligent mechatronics and its transformative impacts on manufacturing. Rapid digital transformation, automation, and artificial intelligence are reshaping the manufacturing industry and beyond. They drive faster, more connected, and sustainable operations from factory floors to transportation systems, empowering industry to enhance productivity, efficiency, and safety like never before. Throughout today's forum, we will highlight research and development capabilities dedicated to addressing current industry challenges and advancing flexible manufacturing systems through state-of-the-art technologies. We will see how our intelligent manufacturing and mobility-related technologies make this evolution of the industry possible. I welcome you to ask questions below. Your contributions are invaluable, and we believe that diverse perspectives will lead to innovation and potential collaborations. Before we begin today's agenda, I would like to welcome Deputy International Affairs Officer and representative of ITRI Southeast Asia Office, Karen Ma, for a few words.
Thank you, Peng Yang, for this opportunity. Good afternoon, everyone. My name is Karen Ma, Deputy International Affairs Officer and representative of ITRI Southeast Asia Office. I'm delighted to be part of today's event. It will be an exciting opportunity to see all of you connect with ITRI MMSL's experts in autonomous and electric vehicles, as well as intelligent manufacturing technologies. These technologies are at the forefront of global industrial transformation and offer great potential for collaboration between Taiwan and Southeast Asia. ITRI is a world-leading applied technology research institute with more than 6,000 outstanding researchers. Our mission is to drive industrial development, create economic value, and enhance social well-being through technology R&D. We are delighted to creating new values, identifying emerging trends, and seeking partner collaboration on possible opportunities while facing global challenges, such as climate change, new supply-demand patterns, urbanization, and aging societies. It is my pleasure to serve as the Deputy International Affairs Officer at ITRI, supported by an outstanding team committed to connecting Southeast Asia's technology demand with innovative capabilities of Taiwan's automotive and manufacturing industries. By leveraging ITRI's global technology cooperation platform, we aim to promote long-term, mutually beneficial partnerships across the region. I look forward to the many connections that will be made with the ITRI Southeast Asia office during today's event. Thank you.
Thank you, Dr. Yang and Karen Ma, for your warm welcome. Next, we would like to invite Dr. Yang once again to provide us with a quick glance at Mechanical and Mechatronics System Research Labs.
Hello, my name is Peng Yang from Mechanical and Mechatronics System Research Labs, or MMSL, an Industrial Technology Research Institute, or ITRI in Taiwan. In this presentation, I am going to give you a quick overview on the capabilities of enabling future smart manufacturing and vehicle technologies. MMSL consists of more than 500 employees, with the majority of them are researchers with master or doctoral degrees. We have more than 1,500 active patents. Our aim is to provide technologies to enhance the intelligence, precision, and green for the industry. We have two major areas. One is intelligent manufacturing, covering robotics, intelligent factories, and also key modules or equipment for the semiconductor industry, and green technologies for different types of industries. The other one is for intelligent mobility. We develop electric and new energy vehicles, autonomous driving technologies, unmanned aerial vehicles, and also railway systems. For the intelligent factory, so we try to connect equipment and materials together with Internet of Things. We also have sensors integrate with our algorithm to quantify the status of the equipment. Then we can connect the equipment together with the parameters. And we also incorporate AI technologies in different stages of manufacturing to control the quality of the product. To integrate all of this, that we can have the manufacturing process smarter. Here is an example. Now we try to integrate systems into a 3D composite braiding system. As a world trend of low carbon or zero carbon emission, we try to reduce the energy consumption in different manufacturing processes with different strategies. The first one is to provide high efficient motors that can be used in different stages of manufacturing, and also low carbon thermal management systems with the energy storage applications, also such as the high-speed flywheel technologies and also superconductor technologies. We also developed new low-carbon, high-efficiency manufacturing processes. Here is an example.
Sinmat microwave annealing technology is the result of a tripartite collaboration between ITRI, National Jiao Tong University, and National Nano Device Laboratories, can process multiple wafers at one time and can effectively control the heating range to avoid thermal diffusion. The technology saves a great deal of time and energy compared to rapid thermal annealing. The frequency of the microwave tubes used in the new technology is 2.45 gigahertz, the same as that of a typical domestic microwave oven. A 2.45 gigahertz magnetron costs only about 1/10 of the price of the 5.8 gigahertz high-frequency microwave magnetron currently used by manufacturers, while its average lifetime is 6 times longer, which greatly reduces maintenance costs.
As you might know that Taiwan is famous about semiconductor manufacturing. We also have a division dedicated to these technologies. So we use multi-physics simulation in different stages of the manufacturing process, such as the plasma etching or deposition, and wave process for advanced packaging. And we also provide grinding polishing equipment that can be used in different materials, including the optical components. We also integrate low fluoride or low carbon equipment in different industries for green technologies.
The following is the principle of the hybrid ALD equipment. The vertical flow field is simulated by multiple physical coupling methods into the 12-inch process chamber through the aeration module, and the special aeration hole design is used to improve the uniformity of the overall chamber flow field. Place the cassette into the wafer loader. System parameter confirmation. By adopting the crossover flow multimodal ALD technology, the thermolysis and plasma bias dual mode is used to enhance the collimation of deep hole coatings, thereby improving the compactness and deposition selectivity of the film layer, achieving multi-composition, high-step coverage, and uniform coating deposition. The robot arm removes the wafer from the process chamber and transfers it to the discharge chamber.
To combine the different manufacturing processes, we need robotic technologies. Over the past 20 years, now we have developed different types of service robotics, industrial robots, AGV, AMRs. We also apply that into different fields, including the surgical fields. We recently have international collaborations with many European countries on the handling with AI-enhanced robotic technologies for flexible manufacturing. That's for manufacturing. Now for mobility, now we developed technologies to fulfill the needs for electric vehicles, from fast charging station, onboard charger, battery pack, energy management systems, vehicle control units, even inverter and motors. So we work with industrial partners to develop the whole system. We are also the first team to have the driving license to drive our autonomous driving vehicles on the real road. Now we have different types of autonomous driving vehicles. We also export these technologies to international partners, such as in Japan. Now we have high-definition map technologies. And in Australia, we now can drive a 35-ton truck on the highway in Australia. That's for ground vehicles. In the air, now we also have unmanned aerial vehicles. We target more on the high payload, specific application, UAVs. Over the past few years, we have developed flight control technologies, high power motor generating technologies, and also integrate into the system with different payloads and applications. In many developed countries, railroad transportation is a good means to transport from one place to another. So we have helped our railroad companies to develop BRT tester, platform screen doors, also intelligent inspection vehicles for railroad track, and automatic painting factories. So we target more on the operational or maintenance systems for railroad transportation. So with this, I give you a quick overview of our capabilities. So if you are interested in any of the technology, feel free to contact us. Thank you.
Thank you, Dr. Yang, for your inspiring sharing. Firstly, we would like to explore the innovative sphere of vehicle. Let's welcome Li-De Huang to talk about design and development technologies for two-speed EV transmission.
Hello, everyone. I am Li-De Huang from the Mechanical and Mechatronics Systems Research Labs at ITRI. Today, I am honored to present our innovative design and the development of two-speed transmission technology for electric vehicles. This system has been successfully validated in real vehicles and transferred to domestic industry partners. As EVs evolve rapidly, traditional single-speed gearboxes are starting to show their limitation. More flexibility is needed to handle both acceleration and high-speed cruising. That's why we developed a two-speed solution to enhance torque, improve efficiency, and extend driving range. Here's the difference between single-speed and two-speed systems. In the current case shown in the right-hand corner, we must choose between torque and speed. But with the two-speed system, we get both. First gear delivers high torque for quick acceleration. Second gear enables efficient cruising and high-speed driving. This expands the motor's effective range and enhances overall vehicle performance. Moreover, the system supports both front axle EVs and rear axle drives. It's scalable and suitable for passenger cars, SUVs, and cargo vehicles. Now, let's look at the specifications. Gear ratio of about 14 and 9.5. Maximum torque output of 3,500 Newton meters. Faster shifting in under 0.4 seconds. Plus, an integrated electronic parking system compliant with SAE J2208. This slide highlights the core technical feature of our two-speed transmission systems. I will guide you through the three main areas that determines its performance and reliability. Firstly, gearbox life calculation. To ensure durability, we perform comprehensive gearbox life calculations using model-based design tools and real-world load inputs. We built a multi-body dynamics model of the system to simulate torque cycle, bearing loss, contact stress, and thermal effects. Using this method, we predict a service life of 200,000 and 4 to 400,000 kilometers. This approach reduces development risk and accelerates design validation. Next, two-speed gear mechanism design. The core of this system is dual gear layout that provides high torque at low speeds and efficient power at high speeds. We optimize the gear structure, tooth geometry, and the torque path to achieve both high performance and compact design. The mechanism also integrates shift actuators and clutches, allowing flexible package for front or rear axle configurations. Third, tooth flank modification for NVH optimization. To reduce noise, vibration, and harshness, we use tooth flank modification techniques, such as profile crowning and microgeometry correction. This adjustment allows meshing impacts and smooth torque transfer as a result. Gearbox noise remains below 60 dB, meeting the quietness expected in the electric vehicle. Together, these technologies make our two-speed system efficient, durable, and refined, ready for real-world EV integration. At ITRI, we don't just build gearbox, we provide complete drivetrain design support. From simulation to full documentation, this slide outlines the range of service we offer to our industry partners. Starting from the top row, we begin with the vehicle-level simulation, including load cycle synthesis, vehicle modeling, and the performance prediction. Next, we move into system layout and the concept planning, such as power flow diagrams and the transmission architecture. In the third row, we focus on subsystem design, covering gears, synchronizer, clutches, electronic parking modules, and housing components. The fourth row centers on the system level analysis, including integration, life estimation, gear contact patterning analysis, structural and model behavior, and NVH performance. Finally, we deliver 4 technical documentation from 2D drawings and the tolerance specification to simulation reports and the complete design verification plans. So, whether you're starting from a clean sheet or upgrading an existing design, our team is ready to support you at every stage of the transmission development process. On this slide, we want to emphasize one key point. We don't just design, we validate. From manufacturing to testing, our team supports the full development cycle of an EV transmission system. Starting from the bottom, we support gear and housing production, including casting, machining, and the finishing of structural components. Moving up to the assembly level, we build and test both individual subsystems and complete transmission systems, ensuring proper alignment, tolerance control, and functional integration. At the subsystem level, we perform gear contact check, shifting tests, parking simulation, and backlash evaluations. At the top, we carry out full system validation, including critical speed analysis, torque performance testing, endurance and efficiency evaluation, and NVH measurement, all under real-world conditions. All test data is documented in detailed engineering reports and verification plans, forming a solid foundation for vehicle-level integration. We have the tool, the equipment, and the expertise to turn a concept into a fully tested, production-ready transmission system. This final slide highlights an example of our two-speed transmission in action. We integrated the system into a Nissan Leaf platform and conduct testing at ARTC Proving Ground. The result was solid. Shifting time was under 0.4 seconds, delivering fast, responsive, and stable performance. The vehicle also successfully passed a 35% slope parking test, demonstrating high torque capability and precise control. Following this successful validation, the technology has been transferred to domestic gearbox manufacturer and is now moving toward commercialization. So what's the real impact of this two-speed system? For passenger cars, we see about 10% increase in driving range, faster acceleration by 12%, over 50% improve in hill climbing performance, and up to 18% increase in top speed. For electric truck, it's just an effective 7% more range, 10% faster acceleration, and more than 50% improvement in gradability. That's the end of my slide. Thank you for following along. We welcome collaboration and are ready to support your next generation drivetrain development.
Thanks, leader, for an incredibly informative presentation. Now let's invite Gao Hongzhu to share introduction to the digital communication conformance test for DC EV charging system.
Hello everyone, I'm Zhu, a project manager, also serve as the electric energy testing laboratory supervisor, dedicated to the EV charging technology at ITRI's mechanical and mechatronical system research labs. Today, I will show the digital communication conformance test for DC EV charging system. This test is crucial to ensure the charging interoperability between the EVs and the DC EV SEs. It's also one of the necessary tested items for the DC EV SE products certification in Taiwan. Unlike simple charging operations similar in reality, when the EV is charged by a DC EV SE, it operates according to a complex process. It is shown in a figure. The DC EV charging process can be roughly divided into the several phases. If you want to charge an EV, first, you need to plug the EVSE connector into the EV socket. That's the plug-in. And next is the auxiliary low voltage supply. When the EV is successfully connected to the DC EVSE, the DC EVSE will start delivering the 12-volt power to the EV before the starting handshake. Handshake is for EV and the EVSE to confirm that they are connected to each other. After the handshake, the EV and the EVSE will inform each other of their required charging information through the message exchange, such as EV battery parameters and the EVSE performance and so on. EV and the EVSE confirm the capability at the charging parameter setting phase. This means EVSE is confirmed to support the EV charging, and the EV can use EVSE to charge. In the charging phase, the DC EVSE starts to transfer the energy to EV. Both the EV and the DC EVSE send and receive the message constantly. In the charging stop phase, the DC EVSE stopped to transfer the energy to the EV and terminate the charging section. In DC charging mode, due to more safety consideration and more complex power control requirement, EV and the DC EVSE should exchange message by applying the digital communication. For each of the charging phases, we have described previously. The related standards or the regulations define the request and the response message with different names used in EV and the DC EVSE. Each message contains multiple parameters or the element value. So how to execute the communication conformance test? In short, the DC charging process is simulated through the automatic testing system, and the various test cases are executed at different phases to verify the digital communication compliance of the EV and or DC EVSE. The test system consists of one EVCC emulator, one SECC emulator, and the other electric power and the major equipment. If the device under test is an EV, the system will stop the SECC emulator. Otherwise, to test the DC EVSE, stop the EVCC emulator. The test cases are designed different depending on whether the device under test is an EV or the DC EVSE. So the next question is, how are the test cases developed? Let's take a combined charging system as an example. First, there are three necessary conditions for constituting a charging communication section between the EVSE during the charge: CP voltage, timing, and the message. CP voltage is used to control the progress of the charging phase or the steps. After completing the plug-in, CP voltage is 12 volt. Then it changes to 9 volt and stops to handshake and the subsequent step. When the CP voltage switches to the 6 volt, start the steps corresponding high voltage power transmission. The second condition is timing. Each stage or phase must be completed within a specified time, and both the EV sending the request message and the EVSE sender respond message must be complete within the time limit. Finally, the messages sent by the EV and the DC EVSE must be correct, including the message name and the element value within the message. Generally speaking, the test case involves adjusting the three conditions: CP voltage, timing, and the message. Intentionally input the incorrect element value or the error message to verify whether the EV or the DC EVSE has a compliance countermeasures. Currently, there are the three types of DC charging system in the IEC standard. The System A, same as the CHAdeMO, this is the system development by the Japan. And System B, that's the GB, proposed by the China. System C, this is what we call the Combined Charging System, or the CCS, jointly proposed by the US and the EU. The IEC, the 61 and the 51-24 standard does not provide a detailed explanation of the digital communication for the three DC charging system. The technical detail of each charging system's requirement and the test case need to be referred to other standards under the specification. For example, if you want to understand the details of digital communication for System C, you must consult the DIN regulation or the ISO standards. The digital communication conformance test is one of the voluntary product certification mandatory items for the DC EVSE product in Taiwan now, and it will be a mandatory item for the registration for the product certification next year. Electrical Energy Testing Laboratory under the Mechanical and the Mechatronical System Research Labs is one of the BSMI designated testing laboratory for the verifying the DC EVSE digital communication conformance. The laboratory has assisted many the Taiwanese manufacturers in completing testing and the verification of the DC EVSE and the EV products, including the Delta Electronic, ITRI Go, China Motor Cooperation, and so on. We look forward to collaborate with not domestic manufacturing and believe that we can provide a huge assistance in the development of the DC charging system digital communication technology.
Thanks, Gao Hong, for nailing every aspect of your presentation. Next, let's invite Geng Hao Zhang to share AI visual inspection platform.
Distinguished guys, ladies and gentlemen, good day. I'm Ken Hao Zhang, Acting Deputy Manager from the Smart Factory System Integration Technology Division at the ITRI. It's my pleasure to present today our latest technological advancement in the AI visual inspection platform. My role involved integrating advanced AI technologies into industrial applications, enhancing both operational efficiency and the reliability of the industrial processes. First, allow me to introduce the AI intelligent probe recognition and adjustment system. Traditional probe identification and alignment tests are often time-consuming and heavily reliant on the manual labor prone to errors. Utilizing AI image recognition, our system swiftly and accurately detects probes, automatically performs positioning adjustment, and autofocus with micro-level precision minus and plus 2 micrometers. Moreover, with big data training, the system accommodates device probe types significantly reduce manual operations and associated errors. Overall, our system enhanced probe adjustment speed by 10 times and reduced inspection time by over 50%, substantially boosting the production efficiency and inspection quality. Next, we have the AI non-destructive drill inspection system. Traditional drill bit coating thickness inspection typically requires destruction testing methods such as scanning electrons microscopes SEM, which take around 20 minutes and generate considerable scrap. Our AI-based solution combined with specialized illumination techniques performs non-destructive thickness measurement in less than 30 seconds, improving inspection speed by over 40 times. Furthermore, the system fully automates aligned real-time quality controls, significantly reduce scrap rate by more than 8%. Our partner companies using this system have successfully enhanced quality and yield, gaining the entry into the supply chains of NVIDIA and Apple. The third system is the Smart Gear Defect Inspection System, addressing the inspection needs for the porous sintered gears with developer and automatic solution combining validation, feeding, multi-viewed imaging, and deep learning inference. The system achieves over 95% accuracy with inspection times per gear under 6 seconds. Utilizing UNet architecture for real-time segmentation, it accurately classifies defects on the gear surface. Additionally, all inspection data are automatically recorded and uploaded, providing comprehensive traceability to support quality analysis and seamless integration into automated production lines. This solution effectively saves over 40% labor time, significantly enhancing quality control for powder metallurgy gears and advancing smart manufacturing. Finally, I would like to introduce our AI magnetic particle inspection technology. Traditional magnetic particle inspection image often contain substantial noise, leading to higher false positive rates. We developed an AI software solution capable of recognizing abstract and blurred defect image by learning complex and diverse graphical features from big data, effectively reducing false positive. Coupled with customized hardware, the system can be instantly integrated into production lines, quickly delivering inspection results. This technology not only aids in high-grade steel production, but also significantly reduces personnel exposure to ultraviolet light, enhancing workplace safety. In conclusion, the AI visual inspection platform not only promises enhanced accuracy and efficiency in defect detection, but also significantly improves workplace safety and product quality. As we continue to refine and expand the application of these technologies, we envision a future with AI-driven inspection system becomes a standard across industries, ensuring quality and safety go hand in hand. We are committed to ongoing innovation and collaboration with industrial partners, aiming to drive digital transformation, enhance smart manufacturing capabilities, and create sustainable competitive advantage for the industries. That concludes my presentation. Thank you very much for your attention.
Appreciate your detailed and well-rounded sharing, Genhao. Ladies and gentlemen, thank you for being with us. To conclude today's event, let's invite Dr. Bingxiang Yang back to share the closing remarks.
As today's forum concludes, I thank you for being a part of this deeply insightful and enlightening online forum. Our collective passion for innovation and dedication to reshaping the future of manufacturing and mobility have made this an exceptional exchange. Let this forum serves as a stepping stone towards forging new partnerships, fostering innovation, and nurturing the growth of intelligent mechatronics in the manufacturing and mobility sectors. I encourage you to stay connected, continue to exchange ideas, and explore opportunities to collaborate. Once again, thank you for your active participation, and I look forward to meeting you again in the future.
Thank you, Dr. Yang. We truly look forward to keeping in touch with our audience and exploring future collaboration opportunities. For those who haven't had the chance to share your feedback, we will leave the QR code on after the event. We have also shared the survey link as well as an email in the description below, so you may write us with some follow-up questions that we didn't get the chance to answer today. Thanks again, and we look forward to staying in contact.